Welcome to Lesson 1.5, Model Types and Selection, Learning Objectives. By the end of this lesson, you'll be able to tell the difference between base, instruct, and chat models, and more importantly, know which one to reach for on any given project. You'll understand how to decode model naming conventions on Hugging Face, navigate the hub to find suitable models, and recognize special variants like GGUF, quantized formats, and multimodal models. These distinctions matter enormously in practice, and getting them right from the start will save you hours of confusion later. Model categories on Hugging Face. When you browse Hugging Face, you'll quickly notice that a single model, say Llama 3.18b, comes in several flavors. They share the same underlying architecture and weights from pre-training, but they've been processed differently after that. Understanding what each variant actually is will determine whether your fine-tuning project succeeds or stalls before it starts. The base model is what comes out of pre-training and nothing else. No instruction tuning, no chat formatting, no alignment. It has one job: predict the next token. That means it's a pure text completion engine. Ask it, what is the capital of France? And it might not answer the question at all. It'll just continue the text in whatever direction feels statistically likely. Base models carry names like Meta Llama / Llama 3.1 Peiki with no suffix, or Unsloth / Llama 3 Peiki. Notice that Google / Gemo22b, it has it at the end. That stands for instruct, so don't be fooled. The absence of any suffix is your signal you're looking at a base model. Here's a concrete illustration of what text completion actually means in practice. Give a base model the prompt, "the capital of France is," and it completes the sentence, something like "cold Paris," correct and useful. But prompt it with, "what is the capital of France?" and watch what happens. Instead of answering, it might pivot entirely, generating something about the first king of France, or launching into an unrelated historical passage. The model isn't broken. It's doing exactly what it was trained to do: continue text. It was never trained to recognize a question and respond to it. That distinction, completion versus instruction following, is the entire reason instruct models exist. So when does a base model make sense? 4 situations stand out. First, continued pre-training, when you want to inject domain knowledge using raw, unstructured text rather than Q&A pairs. Second, custom chat templates, when you need complete control over how conversations are formatted without inheriting someone else's template. Third, pure completion tasks like code auto-completion or open-ended text generation, where you're not doing question and answer work. And fourth, when you have a large dataset, 10,000 examples or more, enough to teach instruction following from scratch. The upside is total flexibility and no pre-baked behavioral biases. The downside is that you're doing more heavy lifting, more data, more training, more work to get useful outputs. The instruct model, sometimes called the chat or SFT variant, has gone through one additional stage beyond pre-training: supervised fine-tuning. That training phase taught the model to recognize instructions, answer questions, and hold a conversation. You can hand it a prompt like, "what is the capital of France?" and it will actually answer you. No fine-tuning required on your part. Model names signal this clearly. Meta Llama / Llama 3.18b instruct has instruct in the name. Google uses it as a suffix, Gema22b it. Mistral uses instruct v0.3. Once you know the pattern, you can identify these instantly. The difference in behavior is dramatic. Ask an instruct model, "what is the capital of France?" and you get, "the capital of France is Paris." Clean, direct, correct. Ask it to write a poem about the ocean, and it writes a poem. It understood the instruction and followed it. That flexibility is what makes instruct models the right starting point for the vast majority of fine-tuning projects. You're not teaching the model what an instruction is. You're teaching it your specific domain, your tone, your use case, and that requires far less data. Instruct models shine when your dataset is small, under 1,000 examples, because they already know how to follow instructions. You're building on a strong foundation rather than constructing one from scratch. They're the right choice when you want to teach a specific personality, domain expertise, or output format, and when you want results quickly. There is one important constraint though. You must format your training data using the same chat template the model was originally trained with. You can't invent your own. Instruct models were trained on a specific conversation format, and deviating from it will degrade performance. The good news is Unsloth handles this automatically, but you need to understand why the constraint exists before you can appreciate the solution. Here's what the Llama 3.1 chat template actually looks like. The conversation is wrapped in special tokens, a begin of sequence marker, then a header identifying the role, system, user, or assistant, followed by the message content and an end of turn marker. The system message tells the model its role. The user turn contains the question. The assistant turn is where the model's response goes. Every single conversation you feed to a Llama 3.1 instruct model during training must follow this exact structure. Deviate from it and the model gets confused. It's like speaking a language with the grammar scrambled. Mistral uses a different template entirely. Instead of role headers, it uses bracket tags to open an instruction and to close it. The user's message sits inside those tags, and the model's response follows immediately after. No system message wrapper, no role identifiers, just instruction and response. This is why you can't mix templates across model families. A Llama formatted dataset fed to a Mistral model or vice versa will produce degraded results because the model has never seen that token structure before. Gemma has its own template format too, using turn tags to delineate the conversation. The pattern is consistent. Each model family defines its own special tokens and structure, and that structure is baked into the model's weights during supervised fine-tuning. This is why template compatibility is non-negotiable. The right template isn't a stylistic preference, it's a technical requirement. Coming up, you'll see exactly how Unsloth removes this burden from you entirely. Here's the good news. Unsloth handles all of this automatically. This code shows exactly how that works. After importing fast language model and loading Unsloth Llama 3.8b instruct, you construct a message as a simple Python list, a role of user, and a content string asking for the capital of France. Then you call tokenizer. Apply chat template on that list with tokenize set to false. What comes back is a fully formatted string with all the correct special tokens already inserted, the begin of sequence marker, the header tags, the end of turn markers. You wrote plain Python. Unsloth and the tokenizer produced the model-specific format. That's the abstraction at work. You describe the conversation structure, and the tokenizer handles the syntax. This same pattern works for every supported model family, Llama, Mistral, Gemma, Phi, without you changing a single line of your training code. Understanding model names on Hugging Face. Fair warning, there is almost no standardization in model names on Hugging Face. Different organizations use different conventions, and the same information, model size, variant type, quantization, can appear in completely different positions in the name. What you can do is learn the common patterns, and after a few dozen models, you'll be passing these names on autopilot. The name MetaLlama/Llama 3.1 8b instruct breaks down into 5 components. Everything before the slash is the organization, MetaLlama, the team at Meta responsible for this model. after the slash. 3.1 is the version, and version numbers matter because they reflect architectural improvements and capability upgrades. 8b is the parameter count, 8 billion parameters, which sits in a comfortable middle ground, capable enough for serious tasks, small enough to run on a single 24 GB GPU. And instruct is the variant, confirming this model has been through supervised fine-tuning and is ready for instruction following tasks right out of the box. The pattern holds consistently across the Llama family. MetaLlama / Llama 3.18b with no suffix is the base model. MetaLlama / Llama 3.18b instruct is the scale up to MetaLlama / Llama 3.370b instruct, and you have a larger, more capable instruct model. Same naming logic, just bigger numbers. Google uses a slightly different structure. In Google / Gemma 29b it, the organization is Google. The model family is Gemma. 2 is the generation, 9b is the parameter count, 9 billion, and it is Google's shorthand for instruct. It's a 2-letter suffix rather than a full word, but it means exactly the same thing. This model has been instruction tuned and is ready for chat tasks. The Gemma family gives you clear size options. Google / Gemma 22b is the 2 billion parameter base model, small and fast. Google / Gemma 22b it is the instruct version of that same small model. Google / Gemma 29b it steps up. The it suffix is your consistent signal across the entire Gemma lineup. Unsloth's naming adds one more layer, the quantization format. In Unsloth's Llama 38b instruct BMB 4-bit, you have the Unsloth organization, the Llama 38b model, the instruct variant, and then BMB 4-bit. This tells you the model weights have been compressed from 16-bit floating point down to 4-bit integers, cutting memory usage by roughly 75%. Crucially, BNB 4-bit models are still trainable. This is the format that makes QLoRa possible on consumer hardware. Unsloth rehosts models from Meta, Google, Mistral, and others with their quantization already applied and their optimizations pre-configured. The underlying model is identical. Unsloth Llama 38b BMB 4-bit is the same Llama 38b base model as MetaLlama's Llama 38b, just pre-quantized and ready to drop into Unsloth's training pipeline without any additional setup. The BMB 4-bit suffix considers the absence of instruct in Unsloth Llama 38b BMB 4-bit means base model. Its presence in Unsloth Llama 38b instruct BMB 4-bit means Mistral follows a similar pattern with one addition, an explicit version tag. In Mistral I / Mistral 7b instruct v0.3, the organization is Mistral I, the model family is Mistral, 7b is the parameter count, instruct is the variant, and v0.3 is the specific release version. Mistral iterates frequently, so the version number matters. v0.3 includes improvements over v0.1 and v0.2. When you're selecting a Mistral model, always check the version and prefer the latest stable release unless you have a specific reason to pin an older one. Special variants. GGUF is a file format designed for running models with Llama DSPP and tools like Ollama and LM Studio. It's optimized for CPU inference and partial GPU offloading, extremely memory efficient, very fast for local deployment. Model names from the block or Bartowski are almost always GGUF. Here's the critical point. GGUF models cannot be trained. They are inference only. The format strips out the structures PyTorch needs for backpropagation. If you load a GGUF model into Unsloth and try to fine-tune it, it won't work. GGUF is for running models, not teaching them. Keep this boundary clear and you'll avoid a very frustrating debugging session. Within the trainable quantization formats, BMB 4-bit is your primary tool. It uses the bits and bytes library to compress weights to 4 bits. It's fully compatible with unsloth, and it's the format that enables QLoRa, the technique that makes fine-tuning a 7B or 8B model fit inside 24 gigabytes of VRAM. GPTQ and AWQ are alternative quantization schemes you'll encounter on Hugging Face. Both are primarily optimized for inference, and while training with them is technically possible, it's significantly more complex. For fine-tuning, reach for BMB 4-bit every time. For deployment after training, GPTQ and AWQ become relevant, but that's a later conversation. Vision or multimodal models accept both text and images as input. They can describe what's in a photo, answer questions about a diagram, or combine visual and textual reasoning. Names like MetaLlama, Llama 3.2 Ju 11B Vision Instruct, or Google/Polygemma 3B Mix 22. They require a different training setup. Your dataset needs image-text pairs, and the training pipeline handles 2 input modalities instead of 1. For your first fine-tuning project, start with a text-only model. The concepts transfer directly to multimodal work, but the additional complexity of vision models is a distraction when you're still building your core intuition. Decision guide: which model variant? For most first projects, and honestly for most projects in general, the right choice is an instruct model, specifically Unsloth Llama 38B Instruct BMB 4-bit. The reasoning is straightforward. It works with small datasets, anywhere from 100 to a few hundred examples. It already knows how to follow instructions, so you're teaching it your domain rather than teaching it how to have a conversation. Training is faster because you need fewer epochs to converge, and the path from I have data to I have a working model is shorter and more predictable. A base model becomes the right choice in specific circumstances. When you have 10,000 or more training examples, you have enough data to teach instruction following from scratch. When you're doing continued pre-training, ingesting large volumes of unstructured domain text like research papers or code bases, a base model is the appropriate starting point. When you need a custom chat template that doesn't match any existing instruct format, or when you're doing pure generative tasks, code completion, creative writing, ASCII art generation, where you want the model's output unconstrained by instruction tuning conventions. Vision and multimodal models enter the picture when your task genuinely requires image understanding. Medical image analysis, diagram explanation, document parsing with visual elements. These are the scenarios where a text-only model simply can't do the job, and you need image-text paired training data to match. Outside of those specific requirements, text-only models cover the overwhelming majority of fine-tuning use cases. Finding models on Hugging Face. When filtering by task on Hugging Face, 3 categories are relevant for fine-tuning work. Text generation covers the broadest range of generative models and is where most fine-tuning candidates live. Text-to-text generation includes encoder-decoder architectures like T5 that are sometimes used for chat. Conversational captures models explicitly designed for dialogue. Start with text generation. It's the most populated category and where you'll find Llama, Mistral, Gemma, and the Unsloth variants. License filtering matters enormously if you're building anything commercial. Apache 2.0 and MIT are the most permissive. Commercial use is fully allowed. The Llama 3.1 license permits commercial use, but with restrictions around redistribution and derivative model naming, so read it before shipping a product. CC BY NC 4.0 explicitly prohibits commercial use. NC stands for always check the license before you invest weeks of training time on a model you can't legally deploy. Every model on Hugging Face has a model card. Treat it as required reading before you commit to a model. It tells you what the model was trained on, what it's capable of, where it struggles, and how it performed on standard benchmarks. For instruct models specifically, look for the Chat template documentation. It shows you the exact formatting the model expects. Check the license section carefully and look for the base model reference, which tells you whether you're looking at a base or instruction-tuned variant when the name alone isn't clear. A thorough model card read takes 5 minutes and can save you days of troubleshooting. The fastest way to find Unsloth compatible models is to search for Unsloth directly in the Hugging Face Model Hub. This surfaces the full catalog of pre-quantized, pre-optimized models that Unsloth maintains, everything from small 1B models up to 70B variants across Llama, Mistral, Gemma, Phi, and more. Each one has already had the BMB 4-bit quantization applied and has been validated to work with Unsloth's training pipeline. You can use any model from any organization on Hugging Face with Unsloth, but starting from the Unsloth namespace means you skip the quantization step and get a model that's been tested end-to-end with the framework you're using. Any compatible model from Hugging Face will work with Unsloth, but the Unsloth hosted versions are pre-optimized and the path of least resistance, especially when you're getting started. Example model selection. Scenario 1. You want to fine-tune a coding assistant and you have 200 coding question and answer examples. The right choice is Unsloth Llama 3.8b Instruct BMB 4-bit. 200 examples is a small dataset which rules out a base. The 4-bit quantization fits comfortably within your 24 GB VRAM. Llama 3 already has strong coding knowledge from pre-training, so you're not teaching it to write code, you're teaching it your specific style, your domain's conventions, your preferred output format. That's exactly the kind of focused adaptation an Instruct model handles well. Scenario 2. You have 50,000 medical research papers and you want to build a model with deep medical literature knowledge. Here, Unsloth Llama 3.8 BBMB 4-bit, the base model, is the correct choice. The dataset is large enough to justify starting from scratch with instruction following. Continued pre-training on unstructured text is a base model workflow by design. You can always layer instruction tuning on top afterward, giving you a medically knowledgeable model that can then be fine-tuned to follow instructions in your specific format. Scenario 3. You want a model that speaks like a specific historical figure and you have 500 conversation examples. The right pick is Unsloth's Mistral 7B Instruct B 0.3 BMB 4-bit. 500 examples is a small dataset. Mistral has strong base instruction following that your examples can build on. The model will learn the personality, the speech patterns, the characteristic phrases from your training data, while retaining its underlying conversational ability. This is one of the most satisfying fine-tuning use cases, and an Instruct model with a few hundred examples is genuinely all you need to pull it off. Check your understanding. Here are 5 questions to test whether the concepts have landed. First, what's the fundamental difference between base and Instruct models? Base models completed pre-training only. They do text completion but cannot follow instructions or answer questions. Instruct models went through pre-training plus supervised fine-tuning, which gave them the ability to follow instructions and hold a conversation. Second, you have 150 examples for a customer support bot. Base or Instruct? Instruct without question. 150 examples is nowhere near enough to teach instruction following from scratch. An Instruct model already has that capability. Your examples just need to teach it your domain and tone. Third, can you train a GGUF model with Unsloth? No. GGUF is inference only. For training, you need PyTorch format models, either full precision FP16 or BMB 4-bit quantized. Fourth, Which of these names indicates a 4-bit quantized instruct model suitable for QLoRa? The answer is Unsloth Llama 38B instruct BMB. BNB 4-bit confirms QLoRa compatible quantization. Unsloth confirms it's pre-optimized for the framework. Fifth, you want full control over chat formatting and have 12,000 training examples. Base or the dataset is large enough, and a base model lets you define your own chat template from scratch rather than inheriting someone else's. Assignment: choose your model. Before moving to the next lesson, take 5 minutes to make a concrete decision about your own project. Work through 4 questions. What is your task? Question answering, chat assistant, code generation, creative writing, domain-specific knowledge, or something else. How many training examples do you have? Under 100, 100 to 1,000, 1,000 to 10,000 or more? Do you need a custom chat template, or is a standard format acceptable? Then apply the decision logic. Under 1,000 examples points to an instruct model. Over 10,000 examples with a need for custom formatting points to a base model. Over 10,000 examples with standard formatting still favors an instruct model for faster training. Write down the exact Hugging Face model name you'll use. For most beginners, that answer is Unsloth Llama 38B instruct BMB 4-bit, the most widely used starting point, fits in 24 GB VRAM, and has excellent general capability. If you want something smaller and faster, Unsloth. If you want to push your hardware with a larger model, Unsloth Llama 3.1 13B instruct BMB 4-bit will work on your 24 GB GPUs. Having a specific model name written down before the next lesson means you'll be ready to run real code the moment we need it. Key takeaways: 10 things to carry forward from this lesson. Base models completed pre-training only and cannot follow instructions. Instruct and chat models completed pre-training plus supervised fine-tuning and are ready for conversation. Use an instruct model when your dataset is under 1,000 examples. Use a base model when you have 10,000 or more examples or when you need custom chat formatting. GGUF is inference only. Never use it for training. The BMB 4-bit format is trainable quantization, fully compatible with QLoRa and Unsloth. Unsloth hosted models are pre-optimized and the easiest starting point. Always read the model card before committing to a model. Check the license, the capabilities, and the limitations. Chat templates are handled automatically by the tokenizer when you use Unsloth. And for your first project, Unsloth Llama 38B instruct BMB 4-bit is the recommendation that will serve you well. What's next? That wraps up the theory section of Module 1. You've now built a complete mental model of the fine-tuning landscape, what fine-tuning is, and when it beats RAG, how LLMs are trained from pre-training through SFT through alignment, how LoRa and QLoRa compress the memory requirements to something your hardware can actually handle, and now how to read model names and select the right variant for any project. The next step is the Module 1 quiz, a chance to confirm these concepts are solid before you touch any code. After that, Module 2 begins the hands-on work, installing Unsloth on your Windows 10 system with those Tesla P40 GPUs, configuring the environment, and running your first model load. The theory ends here. The building starts next. This chart compares base, instruct, and chat models across 6 capability dimensions: instruction following, conversation history, safety filtering, creative writing, code generation, and suitability as a fine-tuning starting point. The scores run from 0 to 5. What the chart makes visually clear is that base models score low on instruction following and conversation, by design, not by deficiency. Instruct models score high on instruction following and safety filtering, which reflects their SFT training. Chat models tend to score highest on conversation history and creative writing, reflecting additional RLHF alignment. The fine-tuning starting point scores are worth noting. Instruct models rate highly here, confirming the guidance from earlier. They're the right foundation for most projects because you're extending existing capability rather than building from zero. This chart plots MMLU benchmark scores against model parameter count on a logarithmic scale, and the trend is clear. Larger models score higher. GPT-4 at the top, smaller models like Llama 3.2 1B at the lower end. What this means practically is that model size is a proxy for general capability, but it comes with a direct cost in VRAM and training time. The reason this chart matters for your hardware specifically is that your Tesla P40s give you 24 gigabytes of VRAM each. That's enough to run and fine-tune models up to around 13 billion parameters in 4-bit quantization on a single GPU, or larger models with both GPUs. You don't need to chase the biggest model available. An 8B instruct model fine-tuned on your specific task will outperform a 70B model on that same task. Size is a starting point, not a guarantee. This diagram breaks down the anatomy of a Hugging Face model name using Meta Llama's Llama 3.18b instruct as the example. Reading left to right, the organization before the slash, the model family after it, then the version number, the parameter count, and finally the variant. This structure is the closest thing to a naming standard that Hugging Face has, and even this isn't universal. Google abbreviates instruct to it, Mistral appends a version tag, Unsloth adds the quantization format. But the underlying components, who made it, what family it belongs to, how big it is, and what variant it is, are almost always present in some form. Train yourself to pass these 5 elements, and you'll be able to evaluate any model name in seconds. This decision flowchart maps your hardware constraints and project requirements to a specific model recommendation. The first branch is VRAM. Under 12 GB points directly to QLoRa 4-bit with Llama 3.23b, a memory-constrained choice that still delivers useful results. With more VRAM available, the next question is whether you need instruction or chat fine-tuning. If not, LoRa BF16 with Llama 3.18b is the recommendation, full precision training for maximum quality. If you do need instruction fine-tuning, the final branch splits on priority, size versus performance. Size-constrained deployments, edge devices, latency-sensitive applications point to the 1B or 3B Llama 3.2 variants. Performance-first projects point to Llama 3. For your setup, 2 Tesla P40s with 24 gigabytes each. You sit comfortably in the middle of this chart. The 8B instruct model is your default, with the option to scale up to 13B or 70B depending on the task. This overview covers the full landscape of quantization and deployment formats you'll encounter on Hugging Face. GGUF is optimized for CPU and partial GPU inference, ideal for local deployment with Ollama or LM Studio, but not trainable. AWQ uses activation-aware weight quantization to get GPU inference quality close to full FP16, a strong deployment format, primarily for inference. GPTQ is the most widely supported post-training quantization format, with broad model coverage, though slightly lower quality than AWQ. EXL2 is designed for high-throughput single GPU inference using mixed quantization levels per layer, a specialized tool for specific deployments. MLX is Apple Silicon only, using Metal GPU kernels for M-Series Max. And BF16 is the full precision baseline, no quantization, highest quality, used with standard LoRa when VRAM. For your fine-tuning work, the hierarchy is simple. BNB 4-bit for training with QLoRa, BF16 if you have enough VRAM for full LoRa, everything else for inference and deployment after training is done. This flowchart maps the process of finding the right model on Hugging Face into 5 sequential steps. Start by identifying your task that determines which model category to filter by. Then filter by task type on the hub. Text generation for most fine-tuning work. Next, filter by size based on your VRAM budget. For your 24GB Tesla P40s, models up to 13B in 4-bit quantization are accessible. After that, check the license. Confirm commercial use is permitted if that applies to your project. Sort by performance using the OpenLLM leaderboard to compare candidates on standardized benchmarks. Finally, test your top candidates with your own prompts before committing. Benchmark scores tell you how a model performs on academic tasks. Your prompts tell you how it performs on your tasks. Both signals matter, but your prompts are the tiebreaker.